All right, guys, this is it. This is our last page of notes, I think, I hope. Page 147. Secant, tangent, segments, plus a few more chords. So on page 147, okay, our objective is to determine segment lengths with circle relationships. Okay, the first thing I want to come back to is that that perpendicular bisector of a chord. So if C is the center of my circle, and AB is any chord, then that perpendicular bisector of that chord will be the diameter. So the theorem is that if a diameter, it should be a diameter, bisects a chord, if and only if it is perpendicular to the chord. So that means that for any chord there is a perpendicular bisector that goes through that chord, and that perpendicular bisector will be a diameter. Okay, and AF will be congruent to FB, and angle DFB will be a right angle. Okay. Now let's do one problem with this. Say I had a circle with center C, radius A or diameter AB, and chord EF, and they intersect at G. And I know that AGF is a right angle. I also know that CB is 5 and EG is 4. Find GC. So they want me to find the length of GC. So what I'm going to do is I'm going to look at this, and I know this whole length from A to C will also be 5 because CB is a radius and CA is a radius. So I know that whole length is a 5, but I don't know where G lands on that and what proportion. What I do know is that EG and FG are equal, so FG will also be 4. And what I'm going to do is I'm going to draw a line that connects C to E. Let's get you guys in a little bit closer so you can see. I'm drawing a line that connects C to E. And what I have in here is a right triangle. So I'm just kind of blowing it up so you can see it. Where G is the right angle, C is the center of my circle, and E is over here. And based on this diagram over here, I know that EG is 4. I'm trying to find GC. The question is, do I know what EC is? Well, from E to C, that goes from the edge of the circle to the center, so I know that's a radius. And I know the radius of the circle is 5 because CB is 5. So I know that this side over here is also 5. So I can use the Pythagorean theorem to find GC. So C is always the hypotenuse. So I have 16 plus b squared equals 25. When I subtract 16 from both sides, I get that b squared is 9, so b is 3. Or GC equals 3. So that's how we can use that. We have to remember that the perpendicular bisector of any chord is a diameter. This is how we can also find the center of the circle. Okay? All right, so let's move on to more interesting things. Let's talk about secant segments. So remember, a secant is a line that touches the circle in two places. So let's say I have circle C. And I have secant ABD and FED. And what the relationship here is, what the rule is that the outside times the whole equals the outside times the whole. So in this scenario here, the outside of DB, or the outside of secant AD, which is DB, times the whole thing, which is AD, equals the outside of the other secant, DE, times the whole thing, which is DF. So if I had an example of this, my badly drawn circle, but it's still a circle. You guys will believe me. A, B, D, E, F. Okay, if I have this particular picture here, and I'm looking at this, and I know that AB is what I'm trying to find. DB is 3. DE is 6. And FE, I'm going to say, is 12. Okay. So I'm going to use this outside times the whole. Idea. So the outside of DA is 3. The whole of DA, everything of DA is x plus 3. And again, when I'm referring to the outside, I'm talking about outside the circle. So DB is the part of the secant that's outside the circle. The outside of DF is 6. And the whole of DF is 18. So I want to find what this ends up being. So I'm going to multiply 6 times 18. 6 times 8 is 48, plus 6 is 100, so 108. Okay. 3 times x plus 3, well, I'm not going to multiply that yet. I'll show you why in a minute. Because I want to do the least amount of work, what I'm going to do is I'm going to divide everything by 3. And I get the x plus 3 equals 36. And when I subtract 3 from both sides, I get the x is 33. So that's what AB is. Okay? Now, if I come back to this, and I look at this theorem about my secants, that the outside times the whole equals the outside times the whole, how would I prove that DB times DA equals DE times DF? Well, again, I see a cross product. Whenever I see a cross product, I'm looking for similar triangles. So here are probably my 2 similar triangles. And I'd have to somehow prove that these triangles are similar to each other. Well, I know they share angle D. the question is, how would I prove that the rest of these, some other pair of angles in here, are equal? Right? So this is a proof that we're going to talk about in class, probably on Wednesday, and discuss proving. We're not going to do it right now because we have other things that I'd like to do with our time. But there is a way to prove that this triangle is similar to this smaller triangle. And we might think about it in terms of angles. So I know this is an inscribed angle, right? So I know it's equal to 1/2 of AE. So I might want to find another smaller angle up here that would prove that they are equal. But that's for another day, okay? So this is one of the proofs that I believe will be on the regions that we will discuss. All right, moving on. Tangent secant angles. So let's say I have a tangent and a secant that intersect out here. So I have tangent AB and secant BF. And actually this same cross product applies where the outside times the whole equals the outside times the whole. But in this case, the outside of the tangent is also the whole. So AB times AB equals BE times the whole thing, which is BF. Okay. So if I had an example of this, okay, and I wanted to figure out, let's say I knew AB was X, BE is 3, and BF, or EF rather, is 9. And I want to find X. So I do the outside of the tangent, which is X, times the, I should write here, find X, right? Outside times the whole, so X times X, because the outside and the whole are the same thing for the tangent, equals outside of my secant times the whole of my secant. So the whole part of my secant here is 12. So I get X squared equals 36. So I take the square root, X is 6. Okay. Try to keep these notes a little bit shorter. We will be doing a proof where we prove this theorem. So if I have A, B, E, F with center C, we could prove that AB times AB equals BE times EF. And again, we're going to be, since we have a cross product, we're going to be working with similar triangles. And those similar triangles happen to be triangle BAF and triangle BAC, or BEC. Or BEA. No, BEA. Okay? And we'll talk more about that at another date, another time. But for right now, what you need to know is that there is a proof involving similar triangles and cross products for both of these that ends up working out. If you want to start thinking about it, please be my guest. We will be proving this in class eventually, just not today. All right, that's it. I tried to keep them short. I think that's all we need to finish out the unit. This is our last night of notes. Signing off, this is Mrs. Northrop. Have a great, rest of the year with me. We're not really done yet. Just done with notes. All right, talk to you soon.